a unique material, one we could no more do without than wood or steel. But in its raw state, it's useless. The compounding of rubber is both a science and an art, to recipes that are often elaborate and always individual. Some have evolved over a century, and many are still closely guarded secrets. They are composed of pigments and plasticizers, activators, fillers, and antioxidants. They depend on mixing times and curing times and temperatures. Above all, they depend on the ingredient that gives raw rubber its unique properties: sulfur. Precisely how it works remained a mystery long after its discovery. But even the simplest product must undergo a process of vulcanization. In the curing presses, sulfur forms links with raw rubber to make it stable and resilient. Once rubber came from the sap of trees growing wild in the jungle. Now these trees are cultivated on plantations, and production is by the ton. Rubber is a polymer, a chain of molecules strung together consisting of thousands of identical units made from carbon and hydrogen. At one time, natural rubber was the only source, but now there is another: petroleum. Man-made synthetic rubbers are now as important as natural rubber. Between them, they meet a world demand for over 8 million long tons a year. Like natural rubber, these synthetics are hydrocarbon polymers, but each is different, and the differences affect their behavior. In fact, we can now design a rubber for a given performance, or tailor it to a particular industrial process. Carpet underlay, synthetic rubber blown to give a sponge. This rubber is a copolymer of styrene and butadiene, first of the general-purpose synthetics. Early rubbers of this type were quick to blow and fast to cure, but slow on the mill. Mixing times were too long. To match the potential speed of blowing and curing would have meant a costly increase in milling facilities. But perhaps there was an alternative. Perhaps the raw material itself could be modified. As it polymerizes, the chains grow at random. The molecules have no regular structure, and final chain lengths vary considerably. Analysis of their weight distribution showed this clearly. A curve typical of a random sample. This needed changing. What we wanted was a way of controlling chain length. If this could be done, we could reduce weight and narrow distribution to give us a polymer more likely to have the kind of performance we were after. First, we had to select a chemical reagent that could do this, and then we had to test it. A difference of as little as 1 part per million would produce a marked effect on molecular weight. Once we had samples, we could study their properties. The weight of this one was particularly low. It behaved well on the mill and broke down much faster. This new styrene butadiene rubber cut mixing times by as much as 20%. Throughput to the calender and curing chamber was now fast enough for the whole plant to be run at maximum efficiency. The manufacturing problem had been solved, and we gained valuable information on the control of polymerization. Control was even more important in developing the next generation of synthetics, polybutadiene and polyisoprene. The problem was to make the units add on to the chain in a regular way. The key to this was a new group of catalysts and a control system of greater precision. Now we were down to fractions of a part per million. The result with butadiene was this: a chain that was extremely even and regular. The units themselves are very simple. There are no bulky side groups, just single hydrogen atoms on the carbon backbone. So the chains are very flexible. It takes very little energy to set them in motion. Because of this, polybutadiene has exceptional bounce and resilience, even at very low temperatures. Compare it with other rubbers after cooling to 65 degrees below zero. First, styrene butadiene. Then natural rubber. And now the polybutadiene. This has some useful applications. In the Alps, for instance, it is being used on the wheels of cable cars. It provides more friction with the cables, and it's also exceptionally resistant to abrasion. Polybutadiene was followed by polyisoprene, which is based on the same molecule as natural rubber. But it's not identical. There's a slight difference in its structure, and this affects the way it behaves. On the left, polyisoprene. On the right, natural rubber. Natural rubber stretches over 9 times its length before breaking, but the polyisoprene continues to stretch, and this property is useful. Elastic thread for golf balls. The thread has to be wound under tension, close to the limit for natural rubber. But add polyisoprene and you increase the safety margin, less breaking and fewer rejects. Polyisoprene answers a production problem, but it also improves the resilience of the ball, gives it greater reach. The fact that polyisoprene is not exactly like natural rubber in other respects limits its use somewhat, but it did lead to a closer study of its properties and the reasons for them. Both rubbers consist of long, regular chains, but in natural rubber, the regularity is almost flawless. When it's made to flow under stress, the chains pack closely for much of their length, and where they do, they tend to crystallize. They start to behave like a solid. The effect of this can be seen by taking a small sample and forcing it through a capillary. At first, the flow is smooth and steady. But increase the force on the plunger until crystallization begins and the flow rate slows dramatically. The rubber extrudes unevenly and may jam up altogether. With polyisoprene, the chains can't pack so closely together. There are fewer areas where crystallization can occur. Where natural rubber began to crystallize, polyisoprene extrudes smoothly. This easy flow suggested some interesting possibilities. It led to development work on a number of industrial processes, discovering the precise amount of polyisoprene to add to other rubbers to improve injection molding. In the shoe industry, even a small percentage of polyisoprene reduces filling time and gives a superior finish. For these yachting shoes, oil-extended polyisoprene allows mold pressure to be reduced, and the shoes have outstanding wet traction. Traction again, and this time, critical. In the automobile tire, rubber's performance is pushed to the limit. And we're always looking for improvements. We know the properties a tire must have, and by using a computer, we can study how the choice of raw materials will affect its performance. It can even show us how a slight variation in compounding can contribute to a better result. From the computer printout, we can trace a series of graphs for tensile strength, resilience, heat buildup, hardness, and so on. With the graphs overlaid, we can pick out the areas of greatest interest.
Do you think we should have a go with that one? Yes,
Here we're looking at a compound that promised particularly good grip and wear resistance. Made from a styrene butadiene with a higher proportion of styrene than usual. Sample batches were prepared. Laboratory tests went well, and a few tires were made. Grip and wear resistance were good, but there was also a problem. Heat buildup was too high.
80.
In extreme conditions, this could be disastrous. The solution this time was in the design of the tire. We kept the new rubber for the outer tread and combined it with an under tread and sidewalls built of an existing compound. The two rubbers are fed to separate extruders. They are then combined and built onto the carcass in the normal way. The new tire was soon showing its paces on the skid pad. The new tire, and for comparison, a normal tread. New tire, standard tire. The wet traction was there all right, but how good was it in other respects? Harsh treatment, but the new tires scored well on both wear and heat buildup. Outstanding skid resistance had been achieved without sacrifice. Even for tires this size, the choice of rubber is important. Several million are produced each week. This is a new type of rubber, revolutionary in that it doesn't need vulcanizing. The tires are made by straightforward injection molding, just like plastic. In fact, what we have here is a totally new class of material, thermoplastic rubber. Each molecule is a 3-block copolymer, polybutadiene in the middle and polystyrene in the tails. In large numbers, the tails associate into clusters or domains. They link the polybutadiene chains and give the rubber stability, the job normally done by sulfur. But with this vital difference: if we heat the rubber and then exert a force, the domains dissociate and the rubber flows. Remove the stress, the domains reform. Unlike every other rubber, this one is truly thermoplastic. For the rubber industry, it opened a whole new range of possibilities. Experimenting with new techniques, applying it directly to carpets as a backing material. Extruding it as a sponge. Blow molding it, trying it in fact in all the processes hitherto reserved for plastics. This is polyethylene film for packaging. One disadvantage: its low resistance to impact. By using two extruders together, we can coat the polyethylene with a layer of thermoplastic rubber. And this makes all the difference. Thermoplastic rubber has already found many commercial uses. For these turntable mats, it means improved quality and fewer rejects. Above all, no time spent on vulcanization. Any scrap or waste can be ground up and used again. Processing is as quick and precise as for plastics, yet these shoe soles have all the advantages of rubber. They're flexible, durable, and they don't slip. Thermoplastic rubber in solution, sprayed onto metal airframe sections. To reduce their weight, the components must have parts of their surface etched away. The rest needs protecting. The whole section is covered, and then the parts to be etched have the coating removed. Thermoplastic rubber is rapidly capturing the world market for this application. It forms a coating that bonds well to the metal, but is easily stripped, and it's highly resistant to the chemicals used for etching. Thermoplastic rubber is one of the latest developments in synthetics, an exciting new material. It marks a big step forward in improving the range of rubbers on which the whole world now depends. "40 years ago, synthetic rubber barely existed. Today, its products are used in virtually every industry. Even 10 years ago, who could foresee a rubber that didn't need vulcanizing? Today, who can foresee its future possibilities?"